Okay, sorry about that. So what I was saying is, for a number like 16, you found fourth roots of 16 previously, I'm sure, and you said, okay, well, there's two fourth roots. 2 is a fourth root because 2 to the fourth is 16, and -2 is a fourth root because -2 to the fourth is 16. And that was our experience with, finding a fourth root of 16. But now we're going to see there's actually two other roots. There's 4 altogether. It's just 2 of them are real and 2 are imaginary. And this theorem will help us find all 4. So 2 of our answers when we do this problem will be 2 and -2, as you'll see. Okay, so the first thing when you do this is to put the number in polar form. So z is, and if this is just 16, then that's r, right? That would be 16 units from the origin in the complex plane. So 16 cosine, and 16 we'd have 0 degrees or 0 radians. So cosine 0 plus I sine 0. I'll use radians. So in the theorem, let's look at the theorem. So we're going to have our, like we talked about before, our 3 roots. It's going to be z sub 0, 4 roots, z sub 0 through z sub 3. So our last subscript is z sub 3. And then we take, I'm going to use this one here. We'll practice both. I like to use radians, but sometimes with the division, it's easier with degrees. On the test, I'll probably put it in degrees for you guys, because here you're dividing fractions. But we'll practice both, because in your homework you might have both. Okay, so what was I saying? So the nth root of 16, or the nth root of r becomes the fourth root of 16. And then cosine of, so this would, because theta is 0, so in the first one k is 0, so you're just 0, or theta over n, which is 0 over 4 in this case. I'll put 0 over 4, but that's just going to be 0, of course, plus I times the sine of, I'll just put 0. So this will equal 2, cosine of 0 is 1, sine of 0 is 0. So that's our first root 2 that we talked about, right? We knew we were going to get that answer somewhere. Then z sub 1. So this first part is the same in all of the roots. Again, that's 4 squared is 16, or just 2, or fourth root. Now, I should talk, you might be wondering, well, why is this just 2 and not any of the other roots? Because there's 4 of them. Remember, this stands for the principal root, and the principal root is the positive real root. Okay, so this has to be 2 here. So now we're going to take cosine of theta plus 2 pi, because k equals 1. So that, in this case, will be 0 plus 2 pi is 2 pi, and divide that by 4. And of course, 2 pi over 4 is pi over 2, so I'm just going to write pi over 2 there. And evaluate these, so we get 2 times cosine of pi over 2 is 0, plus I times the sine of pi over 2 is 1, so we get 1i, so our second root is 2i. And of course we could leave these in polar form, but we want to see them in rectangular form because that's easier to compare when our given number was in rectangular form. All right, so fourth root of 16, and now cosine of, so now we got, this is a 2, k is 2, so we're going to add 4 pi to theta, so 0 plus 4 pi divided by 4 plus I sine, whoops, and 4 pi over 4 is just pi. So this is 2 times cosine of pi is -1 plus sine of pi is 0. So we get -2. That's the second root we talked about. And now we're on our fourth root. Z sub 3 is 4th root of 16 again. This time cosine of, so now if k is 3, you're adding 6 pi to theta. And of course theta is 0, so 0 plus 6 pi over 4 plus I sine, and this reduces to 3 pi over 2, of course. When you're doing this, all of these numbers will end up between 0 and 2 pi. You're never going to get outside of 2 pi. If it's in degrees, you'll never get beyond 360 degrees. And then notice, well, let me finish this here. 2 times, so cosine of 3 pi over 2 is 0, plus sine of 3 pi over 2 is -1, so we get -2i. So all of these numbers, if you raise them to the 4th power, we get 16. So that's what this is saying. So 2 to the 4th is 16, 2i is to the 4th, that looks like a z. Of course, 2 to the 4th is 16, and I to the 4th is 1, so that's equal to 16. Negative 2 to the 4th, we already said that's 16. And then -2i, again, 16. That's why these are the 4 roots. They all raised to the 4th power give us 16. Now I asked to graph this, but I didn't leave enough room. It wasn't a good decision. Let me see if I can find a piece of paper. Here, I got the notebook here. So when I graph this, so I'm going to graph all of these roots. What we should notice here about the theorem at this point is that all of these arguments are equally spaced. Notice this is 0, then pi over 2, plus pi over 2 is pi, plus pi over 2 is 3 pi over 2, and then if you add pi over 2 to that, you're back to 0, right? Our coterminal is 0. The first root is 2. The second root is 2i. I guess that's pretty close. Try to make these equal here. And then -2, right, on our real axis, and then -2i. And what will happen is that, well, notice that all of these are, of course, 2 units away from the origin. That's this part here. And your roots end up lying on a circle of radius r, and the roots are equally spaced around the circle. So if there's 4 roots, they'll be all 90 degrees apart from each other, or pi over 2. If there are 3 roots, then they'll all be 2 pi over 3, or 120 degrees apart from each other. I think we're going to do, yeah, the next one is a cube root, so you'll see that. If there's 5 roots, 360 divided by 5 fifth roots, they're all 72 degrees apart from each other, or 2 pi over 5. And so it's like a wheel almost, and they're all equally spaced around this wheel. So this is 2i, -2, and -2i. So it's really pretty cool to think about that geometrically. Okay, so let's look at the next problem, this time 2 plus 2i, and we're going to find the cube roots of that. So r in this problem will be the square root of 4 plus 4, which is, whoops, not the square root. Oh, yes, the square root. What am I saying? Square root of 8. And then 2 plus 2i would be in quadrant 1. So theta is, and a and b are equal, so it's just going to be pi over 4. We'll do this one in radians as well, and then we'll do the next one in degrees. So the first root, well, let me write this down. So 2 plus 2i is square root of 8 cosine pi over 4 plus I sine pi over 4. You can also write that, of course, as 2 square root of 2. But because we're going to be raising that to a power, it's probably easier just to leave it as the square root of 8. Okay, so there's r. So now we want the 3 roots, right? There's 3, so n equals 3. So z sub 0. So we'll have the cube root of the square root of 8. Or you can use 2 radical 2 if you like. But I think it's easier just to leave it as the square root of 8. And let's use exponential notation. So 8 to the 1/2 and then to the 1/3. So remember, we raise a power to a power. So the modulus here will be the 8 to the 1/6, or the 6th root of 8. So if you use this, of course, you have to apply the 1/3 to both factors. I think it's easier just to use this form. So 8 to the 1/6. Okay, then cosine. So in the first one, you're just adding 0 to this, so you just take pi over 4 divided by 3 plus I sine of pi over 4 divided by 3. So if you are working in radians, remember you're multiplying by the reciprocal when you divide by this number. And so you end up just multiplying these denominators, so you get pi over 12. Cosine pi over 12 plus I sine pi over 12. Since this isn't up here we got, in the previous example, nice arguments to calculate, but pi over 12 isn't as nice. So we're just going to have to approximate a and b if we're going to switch to rectangular form. So let's put these in rectangular form and we'll approximate. Same with 8 to the 1/6. That's not a very nice number either. So what I'll do is, like, one thing I have to switch to radians. I'm in degrees. Make sure we're in radians. So I'll just put in cosine of pi over 12, and then I would take that times 8 to the 1/6. And so that's about 1.37. I'll just round to 2 places. That's A, and then B, we'll do sine of pi divided by 12. And then I'll just go ahead and multiply right away, times 8 to the 1/6, 0.366i. I guess, well, I did 3 places there, didn't I? Just do 0.37. Okay. So there's our first root, and then z sub 1. So this, again, this part's always the same, 8 to the 1/6. That's one nice thing about the theorem, you don't have to recalculate that. Now you start over and say, okay, well, pi over 4, I'll write it out in long form here, pi over 4 plus pi, 2 pi, sorry. And then we're going to divide that by 3. So you go back to the original argument, add 2 pi, and then divide it by 3. And 2 pi is 8 pi over 4. So you end up with, let's put it here, pi over 4 plus 8 pi over 4 is 9 pi over 4. But then when you divide by 3, you multiply by a third and you get 9 pi over 12. So the answer, again, is never going to be bigger than 2 pi once you do your division. So now you've got I sine of 9 pi over 12. And what was I going to say? Oh, that reduces to 3 pi over 4, doesn't it? That's nice, because that's a number I can calculate for sine and cosine in my head, right? So of course this is 3 pi over 4 as well. Cosine of 3 pi over 4 is negative square root of 2 over 2. And then sine is square root of 2 over 2. And 8 to the 6 times negative square root of 2 divided by 2 is negative 1. And then this will just be positive 1 because that's just the opposite sign, plus I. There's our second root. And we have one more to find. The third one, z sub 2. So again, 8 to the 1/6 cosine of excuse me. So now we'll be in the argument pi over 4 plus 4 pi. So you always add an extra multiple of 2 pi and then divided by 3 plus I sine. So pi over 4 plus a pi over 4, or excuse me, 16 pi over 4 is 17 pi over 4. So it'll be 17 pi over 12 in the argument. And again, that one's not a nice, doesn't have a nice reference angle, so we will just use the calculator again. So both of these are 17 pi over 12. I'll go down here. So 8, I need to be able to see this, 8 to the 1/6 times the cosine of 17 pi divided by 12. So negative 0.37 plus, I guess I was going to write it down here, but I'll go over here. And then 8 to the 1/6 sine 17 pi divided by 12 minus 1.37 I. That's my third root. Okay, then we're going to graph these ones as well. I'll use my notebook again. So when we graph these, so 8 to the 1/6 is approximately 1 point, oh, that's the square root of 2. Well, oh, of course it is. I don't know why I didn't notice that. I could have reduced this to the square root of 2, which is, if I write that here, you know, this is 1 over the square root of 2. That would have made that calculation easier. I should have noticed that right there because we got negative 1 and 1. And now I say, of course, because I realize 8 is 2 cubed, and then you raise that to the 1/6, so you get 2 to the 3/6 or 2 to the 1/2. All right, so square root of 2 is our r. Let's just say this is square root of 2. Right, so this is 1. This is about 1.14. So when we do this, well, I'll just put these are 1s. 1, negative 1, negative 1. So if this is a radius of 1, I want to go a little bit beyond that. Excuse me. Let's graph the second one first because that's easier. Negative 1 plus I would be back 1, up 1. So notice that's your r is the square root of 2. So this is z sub 1. And then the pi over 12, and sorry, let me go back. Remember what I said before about 3 roots, then they'll all be 2 pi over 3 apart. So if you understand that at this step here, once you get this argument, you could just add 2 pi over 3 to this. So notice, like, this part is the pi over 4 over 3, and then you're adding the 2 pi over 3. And then once you get that result, you can just add 2 pi over 3 to 3 pi over 4. Now this says 4 pi over 3, but that's because we're adding to still the original. But if you take this one, you would just add 2 pi over 3. So pi over 12 is, you know, over here in quadrant 1. This is 1 point, so this is 2, 1.37, and then up 0.37. This is z sub 0. Again, notice the same radius. And then z sub 2, negative 0.37, down negative 1.37. That circle of radius, if I had a grid, this would look better, but circle of radius, square root of 2, and all of these angles here in between are 2 pi over 3. Okay, so let's do the next problem. We'll work in degrees. So with this part here, I think it's probably nice to work in degrees. It makes it a little easier for you guys. So, get a different pencil here. This time we have z equals 1. We want to find the 6 roots, the six roots of 1. And when you're dealing with 1, when you find roots of 1, those are called the roots of unity. So, you know, if you're finding 4th roots of 1, those would be the 4th roots of unity. 10th roots of 1 would be the, you know, all 10th roots are the roots of unity. Okay, so let's do it for the six roots of 1. So z equals 1 would of course be in polar form. R is 1, and we're going to use degrees. Theta is 0 degrees. So I'm going to follow the form of the theorem here. Add 360 divided by n. But if you understand what we were talking about with the equally spaced roots, you know, you take 360 degrees and divide by 6, the distance between all the roots will be 60 degrees. And so you just have to get the first argument, and then you can just keep adding 60 degrees to the subsequent arguments. And I'll show you that it works out. Okay, so z sub 0 would be, so we're going to take the 6th root of 1, whoops, to put 1/6. You can use radical notation if you like, but of course that's just 1, right? And then cosine of, so it's going to be 0 degrees over 6, which is 0, right? This will of course not be 0 if our root isn't on the positive real axis. Okay, so we get 1, and the cosine of 0 is 1, and the sine of 0 is 0. So the first root is 1. Of course, that shouldn't be a surprise, right? We know one of the roots is going to be 1, and one's going to be negative 1, because those numbers raised to the 6 give us 1. Now our next root, So again, the 1 to the 6, we already got all of that, so I'm just going to put 1 there. So in the theorem, it says take 0 degrees plus 360 and divide by 6. But notice that's equal to 60 degrees that we talked about. So we get 1 times the cosine of 60 degrees is 1/2, and the sine of 60 degrees is the square root of 3 over 2. And so that's, well, that's actually the answer. 1/2 plus square root of 3 over 2i, since we're multiplying by 1. Z sub 2, so again 1. So again, if I put it in the formula, it'll be 0 degrees plus 720 degrees over 6. And that will give us 120 degrees. But notice if you would have just added 60 to this, that's the next argument. So that, if you understand that relationship, kind of makes it easier. You don't have to plug it in here all the time. So cosine of 120 degrees, that's in quadrant 2, so negative 1/2. And then in quadrant 2, sine is positive square root of 3 over 2. I don't need the parentheses. Then z sub 3. So now the next one would be, you take 360 times 3. I'll do one more step like this, but then I'm going to start using the other form. So you get cosine of 1080 degrees divided by 6, which is 180 degrees. But it's just easier to just add 60 to the previous argument. So that's I'm going to do that for now on. So cosine of 180 is negative 1, and sine of 180 is 0. So, well, I guess I'll write it down plus 0i, which is negative 1. Okay, we've got 4 of our roots. We're on to the 5th one, but we call it z sub 4. So now we've got cosine of, so I'll just add 60 to this and get 240 degrees plus I sine of 240 degrees. So the reference angle is still 60. I'm just in quadrant 3 now, so cosine and sine are negative. So I get negative 1/2 minus square root of 3 over 2i. And then my last root, now I'm going to add 60 to this. So I get cosine of 300 degrees plus I sine of 300 degrees. And then notice if you would add 60 to this, you'd be back to where you started. 360 degrees is coterminal to 0. So now we're in quadrant 1. So cosine is positive and sine is negative. There's our 6th root. So if we're going to graph these are all on, these 6 roots are all on a circle of radius 1, space 60 degrees apart, or pi over 3 if you use radians. So I'll graph that real quick. And it didn't say to graph, but let's do it. So let's say this is 1. I'll make this a half. About here, 1, 1, negative 1, negative 1. So we've got 1, and then 1/2 square root of 3 over 2 is about 0.9. So here's z0, z sub 1. Then we've got, let me put this up here. So we graph that one, we graph that one. Negative 1/2, about 0.9, it's about 0.866 actually. And then negative 1, so here's z2, or yes, z2, z3, z4, we go negative 1/2, and then, let's see here, but negative square root of 3 over 2, so here, z sub 4, and then z sub 6 we go 1/2, and then negative 0.9 again, z sub 5. So see how they all line up along that circle where r equals 1. And they're all equally spaced 60 degrees apart. That's it's pretty cool, I think. So what else was I going to say? Oh, and of course, if you find the arguments of these, these numbers, well, you'd just be going backwards, but you get back to 1. This squared plus this squared gives us 1. Right? Okay, one last problem. It's going to be a quick one. Go back to this. It says solve the equation x cubed minus 2 minus 2i equals 0. So this is our variable, of course, x cubed. We're going to isolate that first. So we get x cubed equals 2, add 2 to both sides, add 2i to both sides, so we get 2 plus 2i. So the solutions are the 3 cube roots of 2 plus 2i. There's, of course, 3 numbers we could cube to get 2 plus 2i. We know that now from Dumois' theorem. And we would apply Dumois' theorem here, except we already did this one, that's why it's going to be short. We found the 3 cube roots of 2 plus 2i, so they are, the answers are, where's the other answer? Oh, here, this number, and this number. So from previous page, x is approximately, approximate on this one, 1.37 plus 0.37i. And then the second one is exact, negative 1 plus I. And then the third would be negative 0.37, negative 0.37 minus 1.37i. So, whoops, and this one is an approximation, of course. If we wanted to leave it exact, we would leave it in polar form. Okay, so in a problem like this, if you're solving an equation, isolate x, and then of course there's going to be a power, then you're going to have to apply Dumois' theorem to find the roots. So it's like these problems embedded into an equation. So we are kind of expanding our horizons. We're not just dealing with real numbers here. We're saying we'll take answers that are real or imaginary for our solutions. Okay, well, let me know if you have any questions about that in practice. And the pattern always holds, so it gets easy if you do a few examples. You start to catch on to the pattern. It seems real complicated at first, but it's with the pattern actually works out really pretty nicely.